Namaste. Today's discussion is on thin shock layer theory, right? We had a discussion on thin shock layer theory before, and we have made a discussion by considering the beta by theta is equal to gamma plus 1 by 2, where we have considered gamma is equal to 1. So that become 2 by 2 equal to 1 and the beta is equal to theta, right? So when beta is equal to theta, and we had a discussion that the same equation which is applicable to the shock, streamline, and the body are all can be considered as one. Right? So the basic assumption in thin shock layer theory is like the shock layer is so thin that we really know, right? And thin shock layer theory, we had information that initially the shock wave will be assumed and then the body shape will be calculated. Right? So in that way, if we consider the Maslen's method is a kind of inverse method. Right? Because usually what we do is we have a body shape, then we calculate the shock and the associated phenomena. But in this case, in the thin shock layer theory and using Maslen's method, what we will do is like we will assume the shock wave shape and the body shape that supports the assumed shock. Also, you know, the flow field between the shock and the body is calculated. So let us discuss the steps involved in the Maslen's method, right? So I acknowledge John D. Anderson's hypersonic and high temperature gas dynamics, right? So in the Maslen's method, say let us assume the shock wave shape, right? Here there is a shock wave. Say this is a shock wave that is assumed shock wave, right? Then so in the Maslen's method, we already discussed that it is a kind of inverse method, not a straightforward method. So inverse method meaning is shock wave is assumed under the body shape that supports this particular assumed shock is calculated. Right? So here you have assumed shock and say the psi is a stream function and psi 1 is the stream function which we can calculate at point 1. Point 1 is on the shock and point 2 is in between the body and the shock, which is they can be considered as a point in the streamline inside the shock layer. And 3 can be assumed as a shock, assumed as a body, where we can consider the psi, the stream function that is equal to 0. Right? So we have psi is equal to psi 1 here, and then at point 2 we can have, say here it is 2 and here it is 2 dash. Right? 2 dash is a point in the shock. Right? So let us understand the process. First point is we assume the shock wave shape and then we will calculate the body shape. So once the shock wave is assumed, right, now we know all the flow quantities at the point 1. Right? So basically from the oblique shock relation, we can calculate all the flow quantities behind the shock, right? So point 1 can be calculated. Various quantities in the point 1 can be calculated. So let us write psi 1 that is equal to rho infinity V infinity H1. Right? Then this is the point number 2, right? The step number 2, right? Then consider any streamline, right? Any streamline or any stream function that is psi 2, right? Psi 2 is here, psi is equal to psi 2, and you see, yeah, this streamline is psi is equal to psi 2, where you have a 0 which is less than psi 2 and less than psi 1, right? So we can say that this is psi is equal to 0 and then psi 2 and then psi 1. So we can say that the 0 less than psi 2 less than psi 1. So this identifies a point 2 inside the flow field along the y-axis, right? Inside, we know that in the when we study the thin shock layer theory, we consider this as x, and the perpendicular to the shock, the direction we consider as y, right? So the precise value of the physical coordinate y2 will be found in the subsequent step, right? So psi 1, we know what is psi 2, that also we know, right? So then we will go to the third point and we will calculate. So based on the thin shock layer theory, and now we can calculate the pressure at P2, that is equal to P1 plus U1 by RS, right? So U1 by RS into psi 2 minus psi 1, right? So the physical quantities, all other physical quantities can be calculated, right? Yeah. So this is the fourth step. So pressure at point 2 can be calculated, because I hope you remember this when we have derived in the thin shock layer theory. Right? Now the entropy at point 2 also can be considered, right? So let us say S2 is known because of the streamline at point 2, right? Because the corresponding to psi is equal to psi 2 has come through the point on the shock wave, where the point we consider as 2 dash. So psi 2 dash is equal to psi 2. So when we say psi 2 dash, that is equal to psi 2, that is equal to rho infinity V infinity H2. So from that we can calculate H2, right? That is equal to psi 2 by rho infinity V infinity, right? So H2 can be calculated from the equation, right? Then which locates the point 2 dash on the shock, right? Here. So in turn, S2 dash is also known from the oblique shock relation, right? And because the flow is isentropic along any given streamline, we can write S2 is equal to S2 dash, right? So we can write S2 here. We can write S2 that is equal to S2 dash. So this is the fifth step, right? Now all these are known, right? So now let us calculate the H2. So say the H2 and rho 2 can be calculated from the thermodynamic equations, right? Thermodynamic equations of state, we can calculate H2, which is the function of S2 and P2, right? Similarly, the rho 2 is a function of S2 and P2. So we can calculate the H2 and rho 2. Now calculate the velocity at point 2, right? Calculate the velocity at point 2 from the basic adiabatic equation relation, where the total enthalpy H naught is equal to constant, that is equal to H infinity plus V infinity square by 2, right? So V infinity square by 2, and here H naught is the total enthalpy, and H infinity plus V infinity square is the velocity, and so we can write the H naught is equal to H2 plus U2 square by 2, where we ignore the V2 component, right? So we can ignore the V2 component, and then we can calculate U2. So the U2 is equal to root of 2 H naught minus H2, right? So now all the flow quantities are known, right? All the flow quantities are now known at point 2, right? So if we repeat the preceding steps for all the points along y-axis, so that is between the shock, that is shock at point 1 and the body at point 3 where psi is equal to 0. I hope you remember that psi is equal to 0 can be considered as a body shape starting from our flow over a circular cylinder when we study in aerodynamics. Right? In the basics of aerodynamics, we study that the flow over a circular cylinder on the surface of the circular cylinder where the steam function psi is equal to 0. That gives the body shape, right? So we can calculate, right? If we repeat the steps, then we can calculate all the points on along the y-axis between the shock and the body. Right? Now, the physical coordinate y, which is corresponding to the particular value of phi, can be found by integrating the definition of the steam function. Say the stream function like d psi by dy, that is equal to rho u, right? And then y is equal to we can write from integral psi to psi s, and we can say the same on d psi by rho u. So here the rho and u are known as a function of psi, right? From various steps we know. So this locates the body coordinate where yb is equal to integral 0 to psi s d psi by rho u. Right? So we arrive to the equation where the body coordinate is calculated. Right? So by this way we can calculate yb. Right? So the procedure can be repeated for any desired number of points along the specified shock wave, and hence generating the flow field and the body shape which supports the assumed shock. Right? So also please remember that the basic assumption we have made is this is for the two-dimensional flow. Right? So okay. So this is the process for a Maslen's method, where initially we assume the shock wave and then we calculate or we estimate the body shape. So some of the results calculated by Maslen or taken from the in the Anderson book, you say from the reference 47. In this they have considered the paraboloidal shock is assumed, and then the calculated body shape is shown in the graph, right? So we already know that Maslen's method is an inverse method, where the shock wave is assumed and the body shape that supports the assumed shock and the further flow field between the shock and the body are calculated. That is what the important point we need to remember, right? So here we can say that this triangle, right? So we can say that these triangles or the Maslen's calculation, which is compared with the more exact methods, right? So here maybe here at z equal to 0 is almost in the nose region, right? So it is almost exact when compared to the this is when compared to the exact methods, right? So again, Maslen's method are compared with the Yakura and Sachir in his uh, paper document 47, right? So in the case of Yakura and Sachir, so based on the hypersonic small disturbance theory and the blast wave analysis, right? And also in his paper he has given the corresponding pressure distribution in terms of P by P naught, where P naught is the stagnation point pressure, right? So which I have not given here. So I want to show one example of the the Maslen's method applied, right? So this is what the procedure in the Maslen's method, and this is what the results of the Maslen method, which he compared with other exact methods, right? Yeah. So I stop at this point. Mainly, we need to remember is that the Maslen's method is an inverse method, and it can be used for iterative sense and to calculate the flow over a given body when shock is assumed and the supporting body is calculated. That's all we need to remember, right? So basically, shock wave is assumed and the body is calculated, right? And the steps by Maslen is discussed in the today's class. And the basic for a paraboloidal shock, what Maslen has calculated is compared and shown here, right? It is possible for you to consider a shock and you can estimate the body shape based on this particular shock. Okay. Here I said Maslen 47, it is the 47 which is discussed in the John D. Anderson hypersonic and high temperature. Thank you very much. I stop at this point.